Welcome back everyone to 12.4. In this video we're going to continue talking about cross products, getting into a few properties and applications, but I thought it might be good for us to do a bit of a warm-up problem here. So let's kick it off with finding the cross product, A cross B, and then we're going to verify that is orthogonal to both A and B. So, okay, we have our A and our B given to us over here. Let's go ahead and first figure out what the cross product is. So, A cross B, this is going to be the determinant of this 3 by 3 matrix. Remember, we have I's and J's and K's. These standard base vectors here in our first row, and then A is first here, so the next or second row here is going to be A, so 1, 1, negative 1, and then finally for our third row we're going to write down B, 2, 4, 6. And the way that I always do these, right, well, I'll start off by maybe crossing off the first row and the first column. We have here I. Oh. All right, so this right here is going to be our stuff with I. And then usually I go on and I write also we have minus our stuff with J and then finally plus our stuff with K. And I just kind of write this out first. Otherwise sometimes I forget that the second one here is supposed to be a minus. So, all right, now that I have this written out, let's go ahead and calculate out this determinant of these matrix minors here. So 1 times 6 is going to be 6. And then we have to subtract away negative 1 times 4, right? So we're looking at these diagonals. So negative 1 times 4 would be negative 4, but we're subtracting that away. So minus negative would be plus 4. All right, let's go along to the next one. So first row and second column. And remember, this is our J stuff here. So 1 times 6, 6. Minus negative 1 times 2 would be negative 2. So negative and negative here, that's going to be plus 2. And then finally, our first row and third column, 1 times 4 is going to be 4, 1 times 2 is going to be 2. We subtract those away. And so I usually write my final answer here back in these angled bracket notations. So 6 in our first one, let's see, that's 8, but don't forget that negative sign, so that's going to be negative 8 there. And then finally 2. So this is what I get for our cross product. But now remember, the big property of the cross product, it's supposed to be this other vector that's going to be perpendicular, or another word for that is orthogonal, to both of the vectors that you start off with. And so if you wanted to check if these things are truly orthogonal or perpendicular to one another, we have a great way to do that, and that's going to be using the dot product. So remember here, recalls, so two vectors are perpendicular or orthogonal if when you dot them together, and I guess we've already used A's and B's and stuff like this, so let me do U dot V. So if this is equal to 0, then they're orthogonal or perpendicular to one another. So let's go ahead and check and make sure that we didn't make a mistake, that this thing is orthogonal to both A and B. So I'm going to do the dot product between my cross product here, 10, negative 8, 2, and let's first go ahead and dot it with A, 1, 1, negative 1. And so when I do this dot product, let's see, 10 times 1 would be 10, negative 8 times 1 would be negative 8, and 2 times negative 1 would be negative 2, and when you sum those all together, we get out 0. So yes, these two are orthogonal to each other, right? So A cross B and A, these are orthogonal. All right, how about our A cross B and B? So, okay, 10, negative 8, and 2, and let's go ahead and dot product that with 2, 4, 6. So 10 times 2 would be 20, negative 8 times 4 would be negative 32, 2 times 6 is going to be 12, and so when you add those all together, let's do the positives, 20 plus 12, that would be 32, and we're subtracting away 32, perfect. So yes, this also gives out 0, so they are orthogonal. All right, so that's some great warm-up. Now let's move on to properties. And the claim is the properties for the cross product are almost everything you would hope for, but there's one small caveat that doesn't exactly work like normal multiplication, and that's actually going to be this first one right here. So I'm going to go ahead and star it, or maybe give it some red exclamation points, right? So this is the one that's a little bit different, and maybe you've seen this before if you've messed with cross products or determinants of matrices and stuff like this. But if you do A cross B, a common one for multiplication is that it doesn't matter the order in which you multiply, right? That this should be the same as B cross A. And it turns out, while a lot of these other properties hold and everything, this is one that doesn't work out for the cross product. And the reason actually is coming back to our earlier video here. We were talking about the direction, right? So in this one we have U cross V, and we use this right hand rule, right? So it means that we curl our fingers, first hitting through U, then hitting through V with our right hand, and the direction our thumb is pointing, right? That gives the direction for the cross product. So that's why it's pointing up in this case. However, if you were to do V cross U, so now alternate reality here, and we're switching the orders, so that means our fingers must first go through V and then go through U using our right hand. So if you're using your right hand and you're trying to do it with your thumb pointing up, that's going to be really, really hard, right? There's no way to really hit V first and then U. So you have to turn your hand upside down and kind of you hit V first and then U going in this direction, but that means your thumb is pointing in this downward direction. So actually, V cross U is going to be pointing downward. So this is going to be V cross U right here. So it's pretty much the exact same. It actually will have the same length and everything. The only thing is that it's pointing in the opposite direction. So in this case, we need to modify this. And if you want to point it in the opposite direction, well, it incurs this negative sign here. All right, so that's the main one that's going to be different here. All the other ones are going to be pretty darn similar to what you would expect with normal multiplication. Here's some cross products along with scalar multiplication. The claim is you can kind of factor out scalars, as you would probably suspect. So our scalars here are R and S, and you could first go ahead and do the cross product itself. So we could do A cross B, and then we could take that and multiply it by R and S. Okay, 0 cross A. So if you take anything and you multiply it by 0, it gives you out 0. And remember, the cross product always gives you out a vector, so this actually is the 0 vector. Next up, distributive rules. So the claim is distributive rules do hold for the cross product, but you do have to be careful because now if you switch the order of things, it's different. So this is called like a left distributive rule. So we're distributing A on the left. So A starts on the left and it needs to remain on the left. So I'm going to be very careful and write A cross B plus A cross C. So it's very important that the A stays on the left. Likewise, there's going to be a right distributive rule. Now that, right, it really matters the way in which you multiply, right? You can't just switch the orders back here according to A. Otherwise, you'd be off by a negative. But this will, again, so long as you keep A on the right, B cross A plus C cross A, then this is true. So here are some nice properties. Again, this is a theorem. They do all have proofs, but I mean, they're kind of very long and manipulated matrices and stuff like this. So I'm sorry to say they're not very enlightening proofs, all things considered. But let's go ahead and try to use these things, right? So I'm going ahead and tell you that if you do the cross product between these two things, and while we could calculate it out, right, I'm just telling you that it is -2, 2, 1. Okay, let's go ahead then and quickly then calculate out the following. So here's something very similar. It looks like the only difference is that, right, they're in the opposite order. And so this is basically like A cross B up here, and then we have B cross A. So the claim is these will be off by a negative sign. So instead of it being -2, 2, 1, right, let me go ahead and maybe first start off with, it's going to be opposite of that, -2, 2, 1. And we could go ahead and distribute this negative throughout. And so we're going to get +2, -2, -1. So that's going to be the answer for part A here. Basically, the only difference is that we've swapped the order. And remember, with the cross product, it doesn't give you out the same answer like it does in, darn near every other multiplication that we've seen. All right, one more. Okay, it looks like the second one here, 3, 4, -2, is the same. No changes there. But there's been a change here, right? We have 1, 1, 0 in the original, but here we have 4, 4, 0, right? So that's different. It seems like that 1, 1, 0, it's been multiplied by a 4. So let me go ahead and I'm going to break this up and I'm going to write 4 times 1, 1, 0 times, and this one hasn't changed at all. It's the same thing as if you had multiplied by 1, for instance. You can say, well, why do you even have to put that? And you really don't, but we'll see that this is making it look very similar to one of our properties above. So, looking at this, can you figure out which property from above should we use in order to solve this problem? And the answer is going to be B here, right? Because we have our scalars along with, right, 4 and 1, along with the vectors that we know how to take the cross product of. So if you factor those out, our R and S would be 4 times 1. And then A cross B, right, so here's our A, here's our B. We know what that is. It's this -2, 2, 1. And so we're basically just doing scalar multiplication with 4. And so we're going to get -8, 8, 4. All right, so here's some examples of how you can use, the cross product to kind of quickly calculate out, or these properties of the cross product to quickly calculate out other problems. All right, now let's go into our application here. So the physical application of the day is torque. So you may recall from your favorite physics class, right, some equation for torque is force times the distance from the pivot. And now we're going to talk about, well, what if you have maybe a more interesting angle here, right? So if you're not just, obviously like the normal way that you would use the wrench is that you would push, kind of straight down sort of deal, but maybe you don't get to do this. And you make some other angle, and the claim is we can recreate, a formula for torque. And so the first thing you may want to notice is, right, using this little triangle here, if you wanted to know, well, how much of your force is in this perpendicular direction, right, is perpendicular to this radius. The claim is you can break this up, and because it's a right triangle, it's going to, be related with sine. In fact, it's even talking about it right here. And so the overall magnitude of the torque vector, right, so here's our torque vector right here, is going to be the magnitude of R times the magnitude of F times the sine of the angle between them. And the direction is actually going to be given exactly by the cross product. So, okay, in this case, torque, which I'm going to use this little tau, I suppose, is going to be equal to our R. So this is our radius vector. It's coming out of, kind of where this thing's turning. This is where the nut's turning there. And then the cross our force vector. And you can see if you were to use the right-hand rule going through, I guess these are a little bit strange because R here and F don't have the same starting point. So if I was going to draw this again, I would do R right here, just so we can get the direction correct. So now they have the same starting point. And so if I was to curl my fingers first through R, and then through F, right? Because the order here matters. First through R, then through F. Notice my thumb would be pointing into the page. So it's kind of hard to do this. So here's my right hand. My thumb would be pointing into the page there. And I invite you to hold your hand up to the screen and actually use your right hand, curl through R, curl through F, and your thumb should be pointing into the screen there. And so actually, while we're right here, let me give you a little bit of a bonus theorem. And this is talking about the magnitude of the torque, right? So in general, the magnitude of any old cross product, I'm going to go back to U's and V's for the time being, because it's not just torques. But if you want to know what the magnitude of a cross product is, it's going to be the magnitude of U, the magnitude of V, times the sine of the angle between them. And so actually that's why you get this right here. Right, the magnitude of the torque, which is given by the cross product, right, has this quantity. So the magnitude of, well, we have R and F instead of U and V. So magnitude of R, magnitude of F, and the sine of the angle between them. And so you see, right, a lot of this is all connected. And in fact, you may even recognize that this is very similar to the dot product, right? Kind of if this sine was instead of cosine, right, now you're talking about a dot product. So yeah, like I said, this is all very connected, but let's go ahead and finish this video up with an example. So find the magnitude of the torque generated by the force at the pivot point A in the figure below. So we're pivoting around A. This is kind of where our nut would be, sort of deal. And then we have a torque that's generated by F, so F's being applied here at point B. It's 5 feet away from that pivot point there. And it looks like the force has a magnitude of 10 pounds, right? So we don't exactly have like a grid or anything like this saying exactly what that direction is. We do have this 110 degrees there, but let's try to figure out what the torque would be. Or I guess really here we're just interested in the magnitude of the torque. So the magnitude of the torque, according to this, is going to be the magnitude of R, the magnitude of F, and the sine of the angle between them. So the magnitude of R, well, R, this distance from our pivot, right? So back here, this is where we're actually pivoting. This is where we're turning this nut here. Let's see, this R is kind of the length of the wrench. So this is going to be our 5 feet here. So this is going to be 5 feet. The magnitude of torque, right, is going to be 10 pounds. We have that given to us here. So 10 pounds. And then the sine of the angle between these things. So sine of the angle between them, so it's going to be sine of, let's see, I see 110 degrees. So let's go ahead and write that down. Sine of 110 degrees, so that's going to be 50 times sine of 110 degrees. And this isn't one of those nice ones on our unit circle. So, you know, on a quiz or an exam or something like this, this is how I would leave my final answer. All right, so it seems like we're done, but there's actually 2 more things that I want to bring up about this. Technically, I'm wrong, and actually, I'm right. So I'm going to flip-flop a little bit here on you. The first thing is, right, when you look at this R vector back here, right, if I was to go ahead and move this R vector out, so I'm trying to do the same length as R here, 5 feet, but have them have the same starting point, right? The angle between them, that theta here, is supposed to actually be between these 2 vectors. So actually 110 is not super correct, right? If I just want to plug in using this formula, actually I did a horrible job with math. Not 90 degrees, 70 degrees. So, right, back in our geometry days, we know that, you know, I guess one way to say it anyway is that the angles in a straight line should add up to 180 degrees, or this whole bit about supplementary angles, all that sort of stuff. So I know that has to be 70. All right, so in all reality, probably my final answer should be 50 times the sine of 70 degrees. So this right here really would be the correct answer. And then you can think about it a little bit longer even and say, does it matter? Actually, if you plug these both into a calculator, they give you the same result. And that's quite remarkable. And the nice thing about this, or the reason why they're doing this, is because they're supplementary angles. And so let's go ahead and draw our unit circle really quick. And let's remember, right, 90 degrees is kind of this straight up right here. And that sine is always talking about the height of your point on the unit circle. So if I wanted to draw 70 degrees, right, so 70 degrees starting at this positive x-axis and rotating around, it's going to be something like right here, right? So the height of this point, this right here would be 70 degrees. Or another way to say that is that's 20 degrees off of 90, right? But notice, if you were to go 20 degrees off of 90 in the other way, over here, so you add another 20 degrees, right, you get to 90 plus 20, so this is going to be 110 degrees. Those are the exact numbers that we had, 110 and 70. And notice, because it's kind of symmetric about this 90 degrees, right, 20 degrees either to the right or to the left, notice that the height of these points is going to be the exact same. And that's true not only for 20 degrees, but also if you did 30 degrees or 50 degrees or, you know, however much you want, right? So long as it's kind of symmetric about this 90 degrees, those points are going to have the same height. So in all reality, like I said, I'm going to flip-flop a little bit on you. Initially, we say 110 is wrong and that it should be, you know, 70 degrees inside of the sine. And then if you think about it a little bit longer, it turns out both of these are correct, that they have the same decimal value, and it's because of this symmetry about this 90 degrees that supplementary angles have. All right, so that's it for this video. I hope you guys enjoyed. I'll see you out there.